Now, so, as we mentioned, the total x particular is the sum of xp1 plus xp2, and here's xp1, here's xp2. That would be x1 cosine omega b t minus theta plus x2 sine omega b t minus theta. Now I can combine both into one cosine wave, x cosine omega b t minus theta, that's the original angle, and because of combining the sine and cosine we added the angle phi. Now x is basically x1 squared plus x2 squared, all under square root or power of 1/2. That means that x is going to be the square of x1 plus the square of x2. I'll take the y out and then square the numerator, omega n squared plus 2 zeta omega n omega b squared divided by the square of the denominator, which is omega n squared minus omega b squared, all squared, plus 2 zeta omega n omega b all squared. All of this under square root. So this is the amplitude x of the motion of the mass as a result of the basic excitation y. Now I will define something that's called distance or displacement transmissibility. Displacement transmissibility, which is how much of the displacement of the base is transmitted to the mass itself, how much of y is transmitted to x, and this is going to be defined as a ratio, x divided by y, percentage of x relative to y, how much is transmitted, and in this case x divided by y is this expression right here. I will normalize this expression by dividing the numerator and denominator by omega n squared, okay? That will lead to, right here, become 1 plus 2 zeta omega n squared, that become omega b squared divided by omega n squared, that's r squared, divided by 1 minus r squared, all squared, plus 2 zeta r all squared, and all of this under the square root. So this is the displacement transmissibility, y, the x divided by y. And now I can plot this transmissibility versus the frequency ratio. See what's the effect of the frequency of the base motion on how much the base motion is transmitted to the mass M itself. Now, plotting the transmissibility, displacement transmissibility x divided by y for different values of frequency ratio, we will notice first that when r is 0, all these terms will be 0 and we'll end up with 1 divided by 1. So at low frequencies, low base frequency, it's expected that the mass will follow the base motion. They will move together because it's a slow motion. They will go up and down together, and the ratio is 1 to 1. Now, as the frequency ratio increases r, this term becomes smaller and the amplitude or the transmissibility grows. For zeta equals 0 to grow to infinity. Now, what happens? That's for r equals 1. After that, I will have to stop here and inspect this expression. Now, notice that for this expression to be equal to 1, these two terms are equal. For this expression to equal 1, these two have to be equal, which means that if 1 is equal to 1 minus r squared all squared, then transmissibility, displacement transmissibility is 1, because the numerator and denominator will be equal. And that happens when 1 equals 1 minus r squared, that's the first square root of the square, which means that r is 0. And that's what happened right here. But there's another interesting point, that is, if you take the other square root, the negative square root, 1 is minus 1 minus r squared. That means that r squared is equal to 2, which means that r is equal to square root of 2. So if r is equal to square root of 2, regardless of what the damping is, this fraction will be equal to 1. The transmissibility will be also 1. So if I extrapolate right here, and if this is square root of 2, which is approximately 1.4, then this response, the transmissibility, will pass through this point and then to 0. Now, as zeta increases, introducing damping into the system, the maximum point will be reduced because of damping, but it will still have to pass through this same point of transmissibility 1, because at r square root of 2, regardless of what zeta is, because these two terms will cancel, the transmissibility is 1. So as you increase the damping, okay, this is how it occurs, and they all pass through this point. So you have 1-to-1 transmissibility for 0 frequency ratio, and when the frequency ratio omega b divided by omega n is square root of 2. That results in a transmissibility of 1, which means that both the mass and the base will have the same amplitude of motion, but the phase might be different.